Okay, so this is problem 11.120. It's on page 490. I'll read it first again. An automobile moves around a circular highway curve which has a radius of 90 meters. If at an instant the automobile has a speed of 30 meters per second, increasing at 4 meters per second, or 4 meters per second squared, determine the magnitude of the acceleration of the vehicle. All right, so let's draw a curve. And by the way, this is 11.120. Let's draw a curve that represents the path that the automobile is traveling. So here's the little automobile. Here's wheels on the automobile, and you see now why I'm an engineer, not an artist. Okay? So here's the car moving. It has a velocity that is tangent to the curve. And there's some radius of curvature of the curve rho. Now the car has two components of acceleration that have been described. One of the components of acceleration is a change in the speed, a tangential acceleration. The other is a normal acceleration, something towards the center of curvature of that curve that it's on. Okay? Now they gave us some information. They said that the radius of curvature is 90 meters. And they told us that the tangential velocity at this instant in time is 30 meters per second. So using equation 11.29, we could find that the magnitude of the normal acceleration would be equal to the square of the tangential velocity divided by the radius of curvature, which is pretty straightforward. This is a very simple application of this equation. So 30 meters per second quantity squared divided by 90 meters of radial distance gives you a normal acceleration of 10 meters per second. So the normal acceleration here, A sub n, is 10 meters per second. Now they gave us the tangential acceleration. They told us that the tangential acceleration was 4 meters per second squared, or 4 meters per second every second. Now do you see that since the acceleration of the car has a component in the normal direction and a component in the tangential direction, that you could add those two together vectorially? In other words, you could take this 10 meters per second squared of normal acceleration. Let me move that over here. You could add to it the 4, let me make those a little bit larger. Try to draw it approximately to scale. You could add to it the, which by the way is at a right angle, the tangential acceleration of 4 meters per second squared. And by combining these two vectorially, you would have a total acceleration. Now, how do you add two vectors together when they're at right angles? Square root of the sum of the squares, right? So this is pretty straightforward. It's like calculating the hypotenuse of a triangle. So this would be equal to the square root of the normal acceleration squared plus the tangential acceleration squared. Okay, so when you do that, just plug in the numbers. The square root of 10 squared plus 4 squared, they have the same unit, so I'm not going to bother with that right now. That total acceleration then, probably shouldn't do that, let's just do it this way, is equal to the square root of 116, which is about 10.77 meters per second squared. Now, to be very clear, this component of the acceleration changes the speed of the velocity, the magnitude component of the velocity. This component of acceleration changes the direction of the velocity so that the vehicle remains on the path. Questions, comments? Okay, so straightforward application of 1129.